Okay, we'll go and get started here. Let me open us up in prayer and I'll let you know what we're going to be focusing on today. Dear Heavenly Father, Lord, thank you for the chance to be sharing this material with the students in this course and the chance just to be part of their educational process here at APU. Pray that the material will be clear, it'll be enjoyable, and that it's going to contribute to help them get the degree of their choice, getting the job, or perhaps going on into grad school or opening a business of their choice. And pray that you would also help them in their spiritual formation, Lord, that all the time they're getting a chance to study scripture, it's going to be meaningful and they'll be able to cherish those topics in their heart and utilize them in the future as the events and things come to place where that would make sense. We ask all these things in Jesus' precious name. Amen. Okay, well, we're going to be focusing today on the last of three chapters that are dealing with instruction set and a assembly language. And so I'm just going to quickly just review the kind of things that we talked about in these last two chapters. And so chapter 13, we are looking at the characteristics and functions that we could be seen in the instruction sets. How are you going to put in values for numbers and characters? Those are some things that we got a chance to be considering with that, and also trying to think these two different architectures, x86 and ARM, architectures for how they do that. Then in chapter 14, we were focusing on address modes and formats. And so there is one chart that I'll show you real quickly that talks about these different types of addressing modes. And so this is a cartoon that kind of gives an illustration of that. And one of the things we'll talk about in this chapter, we'll have an example and we'll be talking about immediate. And so we're going to have an immediate field for an ARM instruction that I'll be trying to get into a little bit more in detail. So thus we have to be thinking about how we're going to have those different addressing modes. The formats for an x86, they have variable length instruction formats. For ARM, it's always the same. And so when you start to encode those bits, it means something specifically. And so we're trying to now get some insight into what that exactly means. And so now we're going to think about assembly language. We'll be thinking a little bit about compilers, cross compilers, different types of assemblers and linking that has to take place. When you compile a program, say you're trying to do it in C or C++, maybe you've run into these things where you have like a linker or an assembler. Even if you have compiled code, it's relying upon the libraries that are associated with the things that are going on behind the scene that they need to make sure that they're there. So I'm going to be focusing on mostly just a few charts, but I am going to go over the majority of stuff here. So this is going to be a little bit hard for those in the back to be seeing it. And so this is something that's in our textbook. And so you can refer to Stalling to see this on table 15.1. But this also are the key things that we're going to be covering. And so we have like these various terms: assembler, assembly language, compiler, executable code, instruction set, linker, loader, machine language or machine code, and object code. All of these have slight differences in what they're actually focusing on. And so we talk about assembly language. And so this is like trying to put information in a format that's easier for us to comprehend, but it's not in a format that the computer can understand. So I'll just cherry pick a few for now. An instruction set, this is the set of things that we're able to do and be able to command a processor to accomplish. Anybody remember the three-letter summary, the acronym, if you will, for part of the CPU that does all of the processing. And it begins with an A. Anybody remember? ALU, yeah. And so the instruction set, one of the things it does, it instructs the arithmetic logic unit what's it going to be accomplishing. And so there's a difference between assembly language and machine language. Machine language is when it's actually just ones and zeros. And the next chart, you'll get a chance to be seeing this. And so a linker, when you're compiling it, there's things like libraries and other things that need to be added to it. For a compiler, you can have multiple passes. And so it does some things in the first pass, a little bit more, and completes it in the second pass. I'm not going to talk about that in detail, but I just wanted to be mentioning that. So let's consider how we would program the statement n equals I plus j plus k. And so we're going to have 4 renditions of that. And so first of all, this A, this is it in binary. So this is what a computer sees, and this is all it can understand. And guess what? That's going to be tough for us to figure out what exactly that means. And so thus having these other alternative formats can be useful. So anybody remember what hexadecimal is as compared to binary? What's the relationship between these set of numbers and what we're seeing over here? Anybody want to? Yeah. Yeah. So you see these 4 digits represent this digit here. Okay, so if you can start to be seen as anybody want to try and what is the decimal? What is this in decimal? What does that value represent, or integer? You can, okay, I'm seeing good. So sometimes it's fairly straightforward. So 2, 2, so we can see 2, 2 there. Then we see here. So what's this first digit represent? How many? If I put that into decimal or integer. So the first one is 1, 2, 4, 8. And so 8 plus, what does this represent? Yeah, so 8 plus 4. So that means it's 12, right? As an integer. And guess what? There isn't a single digit for 12. But when we put it in hexadecimal, there is. And so that's what we see here. That's where we're having that C. So you can see this is a lot more compact way of having all these bits. And so this can be fairly useful to giving a sense of that. Another thing that we're seeing is we're going to see commands are up here, and then there's data fields in another part of memory. Okay, so we're moving from from the closest to the way the CPU understands things, and then moving up to a higher abstraction. So this is in hexadecimal. Now we're putting in the name of the commands, and so LDA, load, add, store. So we have 4 different data commands, and here this is for this simplistic way of coding it, this is just trying to be stated, this is data. So we actually have 4 variables, I, J, and K, and the output goes into N. And so this is now assembly program. This is what we produce in our Mars MIPS emulator, and we can be seeing this. And so this is like the first statement. So if we wanted to have a loop, we would go back to formule. And so the first thing is we load I. So we're not seeing multiple fields. So it doesn't say load I somewhere. So this is like putting it on the stack. And then you add what's in J to what's on the stack. So 2 plus 3 is what? 5. Okay, so that's now what we have on the stack. And then we add K. So what is the value for K? Anybody see where that is? Yeah. And so then we have what's on the stack, which is 5. 5 plus 4 is what? Okay, good. So that's what we have here. So we finally get the summation of all of these things put into the last location, just say it's a register. And so that's what we have here. So you're getting a chance to see what's going on. We have a mnemonic for what is the thing that we're executing. And so here we're seeing that laid out. We're having where it's pointing to the register. So here you're going to be loading, and so this is this register 201, here 202, 203, 204. And so that just gives you a little bit of a perspective of what's going on in the assembly language. You guys tracking that? Does that make sense? Any questions? That's one of the charts I wanted to dwell on to have us make sure that we're tracking along with that. So just we have a couple charts that talk about the pros and cons of assembly language. So assembly language is a programming language that is one step away from machine language. And we're seeing that here. This is the binary program machine language. This is assembly language. We can actually read this, although it's not as easy as a higher level language. Typically, each assembly language instruction is translated into one machine instruction by the assembler. We saw examples in the Mars MIP simulator. Sometimes it's multiple, maybe 2 or so. The assembly language is hardware dependent. So let's say, for example, that this was done for an x86. And so we come up with the machine language for that. This is going to, if this was done for a MIPS ARM processor, would that work on an x86 processor? Right, correct. So even if we were going to be, yeah, that's just indicative of what I'm trying to have us to be thinking about. So assembly language is a hardware dependent with a different assembly language for each type of processor. Assembly language instructions can make references to specific registers in the processor, include all of the opcodes of the processor, and reflect the bit length of the various registers of the processor and operands of the machine language. So there's a lot there. And hopefully after going through a couple of charts, you'll get a chance to be seeing it. So basically in a one command line, so here we see something fairly basic here, load I. All of these different things that we're mentioning are taken into account. So disadvantages, it can be hard to program in assembly language. Probably don't want to be doing it for average programming. This is one of the reasons why it's really important to have a lot of comments in your code, because it's not going to be intuitive as it is for a higher level language bit of code. But there's advantages. You can make things go faster. It can be helpful if you have like an embedded system. And so you don't want to have a lot of overhead for something like that. It can be optimized for size and speed. So you have limited memory. You want it to go fast. Thus, you can put things in assembly language, and all that's going to be helpful. So remember, there's a difference between machine language and assembly language. Machine language is this, ones and zeros, that's machine language. And assembly language is a thing that's more readable, that's approaching something like that. So sometimes it's easy to get those two confused. So we've talked about what a assembly language command looks like. And so here is one of the ways that you can be thinking about what it all composed of. You can have a label, so you don't have line numbers. So you have labels if you need to branch or something like that. That's going to be helpful. You have the opcode, so add, load, store, something like that. And then you have operands. It can be one or more registers, or it could be a value like immediate. So you just be putting, you're going to load into a certain register that's going to make it query what's in the console, and so you load 10 into a certain register. We saw that in the Mars MIPS emulator we use. And finally, this is a real important part. It's optional, but I would recommend that you don't leave those out. So then we just have some more details of each one of those, the labels. So this is, it's the equivalent to an address, and so you can branch to that. And so that's going to be a helpful thing. The mnemonic is trying to, this is where you specify what is you're going to be configuring your computing environment to be able to do. The operands, this is where you have the registers or some other value that's associated with what you're trying to explore. Does that make sense? So we're just trying to expand and think about each one of these areas here in a general assembly language statement, and what is the structure. Okay, well, we then can get more specific. And so this gives a little bit of the insight of how things evolved with the x86 approach. And so you can have these different terminologies, a high, a low. And so you can just have 8 bits represented there, or put it together, and that's called AX. And then when they extended it, now with 32 bits, it's called EAX. And so we see that same convention for A, B, C, and D. So we have these 4 general purpose registers. And so thus you can be backward compatible to the way things were with previous versions of compilers. Then we have 4 more registers that are 32 bits long. And then we have some other type of registers. So it's not every register is the same, but you're using some registers for one purpose, others for so anyway, they're not all made the same. We see that both in the x86 architecture and the ARM architecture. So I already mentioned the comments, and so it is something that can be really useful, probably the most useful, because it can be more challenging to just by your naming conventions to, in a sense, try to be offering some level of commenting. It's not going to be as prevalent for assembly language. There's also pseudo instructions that it's going to be telling you things that need to be done before you finally convert it into just ones and zeros. You have to be loading libraries. There's other kind of things that have to take place. So you start here and you eventually get over there. So that's something that comes up that needs to be considered. I'm not going to spend too much time on this, but the net-wide assembler, NASM, it's a sample assembler, so it's not x86, it's not ARM, but it has some of the characteristics that are the things that will be seen in those two particular architectures. And so Stalling uses that as a way to be thinking about it, including things like having macros that you can be doing. So having things that are contained in some aspects of the code that you're looking at. And so you have to unpack that first before you're finished in the assembling the compiling of a program. There's directives. We've seen directives in our Mars MIP emulator, syscall, noted a label that it's data or stuff like that. So those are some things that have a little bit of familiarity to you. The assembler makes use of the x86 int instruction to make system calls. And so ARM does it differently. So you load it into a certain register and then you do a syscall, and then it does, it looks into that register for it to figure out what you're going to do. And so there's a lot of these different registers that are used in the x86 architecture. Okay, well, let's think about how how well are we writing that code? And so here are two examples. One was from a high-level language compiler. And so this is auto-generated. So C, C++ generates some assembly language code, and this is what it would look like. And this is saying how we would do that if we were writing it by hand and being a little bit more efficient. So what do you think? Which one do you think would operate faster? Anybody want to do my convention? So we got one vote on this side. Anybody else want to make a vote? Which one do you think is going to be performing faster? One on the right, one on the left? Okay. What makes you say that? Mm-hmm. And so they're equivalent. So with some of the courses you've taken, CS 260 or CS 160, big O notation, how efficient is it? This is going to be taking a lot more horsepower to make it work. So thus you can see a motivation for writing it by hand, or using some more sophisticated tools. It's going to take half the space and it's going to go faster. So those are the advantages you want to be taking, to be utilizing. And so, yeah, you could just do a compiler that goes from C or C++ down to assembly language, and it has to be done for a specific architecture. But this is going to be going a lot faster if we do it like that. All right, well, let's do a comparison between a C program for generating prime numbers. And you can be seeing that the number of lines of code isn't that many. And then we could go over to this, and you can be seeing this in the textbook. Here would be an assembly language equivalent for that. And so this is an x86 way of doing that. Anybody want to, how would you be able to, if somebody didn't tell you, what would be some of the things you would be looking for to see if this was x86 versus an ARM assembly language program? Anybody have an idea? Well, I'll give you a hint to start out with. And so anybody have an idea what that is representing? It's a register. Okay. So does that look like the naming convention that you've seen in an ARM or as an x86? Anybody have a recollection of that?
Also, like two different, you can remove like a register, like remove the contents of certain register to another.
Mm-hmm.
Um,
Yeah, so ARM and x86 both have registers, that's true. But they have specific names for those registers. Let's just go back to a chart that we were just showing earlier. And so I'm trying to just go through this a little bit slow so we can pick some of these things up as we go along here. So we can see those kind of names being that we're seeing here, and this is for an x86 architecture. And so that's one of the ways that you could start to pick up that this is an x86 versus an ARM. Okay. There's some other subtle things. You could see that they're trying to make things like the high level language, which is perfectly fine. You want to make it as easy to read as you can. You can see that the kind of commands that they have, having a while statement. There is no such thing as a while statement in assembly language, but you could mimic that. It's going to take more lines of code. You can have the equivalent of printf and scanf, and so they try and have those kind of conventions to make it match. You know, here's scanf, and so we're doing various call. You're reading an input that has to be defined. And so those just are some examples. So handful of lines of code to be doing it in C. And then it takes 2 pages to be showcasing how it would be done in assembly language. So the takeaway from that is just, is this the kind of thing that we would want to do in assembly language? Anybody have a thought about that? What would be the reason why we might want to be doing this in assembly language versus C? Anybody want to give your 2 cents on that? Go ahead.
It's such a repetitive task, it's like somebody maybe great.
Mm-hmm.
You just can do it so much faster than the compiler language.
Yeah, so you start to be thinking about your software design. If you're going to be doing it once, 10 times, maybe you don't need to, but if you're 1,000,000 times, it keeps coming back to this. This is key to your project. You know, having this done in assembly language would be something that you would want it to take advantage of. Okay, so that's just another point to be thinking about. I'm going to skip over some of these charts here. Here's another example. So once again, anybody want to venture a guess if this is x86 or if this is ARM?
Doesn't ARM use like the LI, like the load?
Yeah. Yeah. Yeah, so you can be looking at the registers, you can be looking at the way that they do their naming convention. Some things are similar, like .text, we saw that, .data, we saw that. Registers are different, the naming convention is different. And so those are just some subtle things that we can be seeing here. So for moving a string, that sounds like something that you might do a lot. So maybe once again, that would be a good example of something that you would want to be doing in assembly language. So you're just seeing some more examples. We didn't really focus on x86 because we're using the Mars MIPS emulator. Anybody ever heard of a cross assembler? Is that something you've heard? I think some of you guys. And so let's say, for example, you're building software, writing software on your computer, but you want it to run on your iOS or your Android device or something else. You can be having a cross compiler. And so what it's going to do, it's going to be creating a machine code that you then load on your machine. So you can think like your Arduino kits. This is what we do. It's like you write the program, it loads it into the Arduino, and it doesn't load the source code, it compiles it. You have to compile it, and then you can load it into the Arduino unit. So let me see, anybody bring their Arduino kit today? Okay, good. Maybe we'll pull it out in a few minutes just to give some people a little bit of show and tell, and we'll continue to be doing that as we progress. Isaiah was kind enough to show me where he was at with his project, and we will definitely want to make some time that people can be sharing some of the neat things that you are creating. So there's various kinds of assemblers. Sometimes they're single pass, sometimes they're multiple pass. And so you have to compile things from assembly language into machine code. Then you have to put libraries together. All of those are the kind of things that need to take place. And so this flow chart just to gives you an idea of what's taking place for a 2-pass assembler. So you read from the source file. That's the thing that we start out with. We've seen some examples of source code like here. Does it get to the end of the file? Okay, no. Are there any things that it needs to do as it's reading that there's more things that need to be unpacked or added to it? And so this is just some of those details. You have some iterative processes that you end up going into to finally get to a point where you got all of the lines of code in your program working and you're ready to upload it into your Arduino unit, upload it into your iOS or Android device, whatever it might be. Well, I'm going to talk about a specific command in more detail here, but let's look back for one of the charts we had in our last chapter, just to give a little bit of context. And so we can be thinking about a general type of command. We saw in this chapter a couple of ways of thinking about it. So you have the mnemonic, the opcode, and one or more operands. So that was one of the ways that we could be seeing that. We saw this chart where we have like the opcode and an operand. We see that being played out there. But now we see the characteristics for an ARM instruction. They're all the same size. So this is all showing 32 bits. And so we have an opcode, we have one or more operands, and then we can have some other things that are part of what we're looking at, like immediates. And so this is where we had the information from our last chapter. And so let me just go to that real quickly, and I'll come back to this in a second. So this is like we're integrating a lot of things together. And so this is where it's showtime, you know, for an instruction, we need to be doing all of this. And so what we see with immediate, we have the opcode. And so we're going to load 10 into register 1. And so this just has 10. We have to translate that to what it would mean in binary. And that's how we have it. And then we have these other types of addressing modes that we have already had a chance to have a brief introduction for. Now, when we look at the details where we're trying to unpack at this point, we're reflecting back on this chart. And now let's go to this one. This is the one I wanted to focus on in a little bit more detail. So this is figure 15.9 in the textbook. And so here is a command, adds. So this is a special kind of adds. And then we have 2 registers. And so we're doing an immediate 19 into with the content of register 3, and then putting that resultant back into register 3. So that's what we're trying to accomplish. And so we have an opcode. We have other types of things that you could roughly kind of say this is all trying to characterize what the opcode is with each one of these values. We have 2 registers. It turns out that we're using the same register. We have immediate, so there's a specific value 19. And then we have all these nuances. Anybody remember we talked about shift registers and then this idea of rotating? Anybody remember what rotating means?
Changing opcode from area to another, thing like that.
Well, saying like we have these bits here, and if I had a rotate, if I was to shift over this, instead of going away, it's going to be putting that value over there. Shifting would just be moving it out of the register, and then you would be putting in zeros. And so gradually you would get this whole register would be have all zeros. So you can see there's a lot of stuff that's going on. So this is for this particular command. So here is, it's using the always condition code. So, and so that is 1110 is the always condition code. Here we have a flag, S, and so that means setting it to 1. So arm and thumb, which is like another way of talking about ARM commands, but with a shorthand process. Data processing instructions only update the condition flags if you append an S suffix to the mnemonic. So thus we see this. So we have this bit that's set. And so this is where we can see there's a lot more complexity of what's going on. So here we can be seeing, here's the opcode. All zeros, 1, 2, 3, 4, and 5. So that gives you a variation. We can see here's a difference. These have the same opcode there. 1 has a 0, 1 has a 1. So thus we're getting more specific on bits that are intertwined all the way through this instruction, a particular instruction. We can have 2 types of immediate. You have an immediate, you can have an immediate with an offset. And so the one that we're focusing on is this one. The always condition and 001. 001. And so this is the one that we're coding for in this particular example, that getting into a little bit more detail. You guys following what I'm talking about there? Does that make sense? So let's take it at a very high level. There's the highest level, I just wanted to have you think there's a lot of complexity in an instruction. Remember how we program an ALU? You have two inputs, you have control lines that tell you what you're going to do with those two inputs. So we see those types of things and some other kind of more complicated things. Guess what? We've been developing compilers for a long time now. And so there's these various parts of the complexity that are included that we now can be utilizing. So that's probably the highest level takeaway that I wanted to have you be thinking through, and hopefully getting a better sense of what we're trying to capture in this chapter. Any comments or questions on that? So we have a really basic type of assembly program that I showed you here, 4 different ways of thinking about it. We have the different parts of a statement, label, the opcode, the operands, and any comments. All of those are important for us to be thinking about. Then we had a specific command where we're showing what those ones and zeros mean. And so the person that designed this architecture has to make sure that each one of these are defined, because that's what a computer is, that's all a computer is going to be able to do with, is just ones and zeros. This is what a computer looks at, and this is what it processes. And it has to be put into that very basic type of construct for it to get it and to process it correctly. Okay, so that's kind of the takeaway for the main points for this chapter I wanted to make sure that you have. So I mentioned there's can be these various types of assemblers, a one pass, and so that means it's got to do it all in one step. This was a 2-pass assembler. So this would be another approach that you can be having. And I'm not going to spend as much detail focusing on these things. I've tried to give a sense of this as we're going through the other areas here. So you have to link and load everything. Not everything is just in those lines of code. And so there's things based on the construct of what's made available in that assembly language that needs to be all hooked together for it to finally process and then complete. So those are the big items. Any comments or questions? Well, you guys have been doing some assembly language programming now. Any observations that you've started to get out of this? Anybody like it? It's okay to be honest. Say if you don't like it. Maybe I'll put this, how many people don't like it? Okay. So chances are you're not going to be doing too much assembly language programming. That's fine. I actually did it on a project when I was at USC. I was working with my physics professor, and they had this quantitative mass analyzer of solids. And so it didn't have any programming. It was just basically, they had an interface that you could put a card and you could program. And so we created a way of having it do certain functions. So there's certain control lines. I know we have a couple of engineers in the course. And so you have like these, the rising edge of a signal is going to cause it to actually turn one function on. So either you're going to go from sampling or just doing a first image before you do that, the destructive, what is that, that top layer of that, substrate that you're trying to be thinking about. But maybe, and probably a lot of the times doing this type of approach, just doing it in C, say that's actually going at a lower level than your primary language. Maybe you might be mostly programming in Java, or something like that. Instead of going down into assembly language, you're going to have to be making that choice. So you're writing programs in your Arduino, you're compiling and then loading it into your Arduino kit. And I think at least one of you guys brought your Arduino kit. If you did, feel free to pull it out and we can have a little bit of show and tell here for a few minutes while we're the latter part of our class. Thus, this is the reason why it's helpful for folks to be here in person on Tuesday. Have you ever played with an Arduino kit before, or is this all brand new?
Before, I actually don't even know.
Oh, wow. Well, you can do the honors, and it looks like you took it out of the overall packaging, and we could start to, you mind if I just put it up here for a second? I'm not going to be tearing it apart too much, but I know this is where it can seem kind of pretty overwhelming and intimidating. And so this is your Arduino board. So this is the, yeah. And so, you're going to be plugging your USB connector. I think that maybe that's not the normal cable that comes with it. This is actually has a lot of extra kind of features that aren't totally necessary, but for some of you, like Isaiah, they're getting a chance to be exploring a little bit more detail as a result of having those extra capabilities. This is your wiring board. And so what you're going to be doing is you're going to be plugging these wires into this board and connecting it with particular pins on your Arduino. These funny looking things, these are all of your resistors. You might remember me mentioning that name. You have a couple other devices here. You have your light sensing photo diode. You have some push button switches. This would be something that's actually a lot of fun, but it's a little bit more complicated, just having a display. And so maybe do something more basic before you jump into something like that. And we have a more just a 9, like your digits. This would be simpler to program than this. Then this would be something more like what you would have on your console that would be reading out on your computer. And so those are just a few things that I'm going to highlight. So most basic things, this is, you're going to be plugging it into USB for your computer. And so even if you, for like Thursday, just try this, make sure that you have downloaded the Arduino IDE, plug this into your Arduino, and then plug the other end into your computer. And let's start to do some basic commands together in our Thursday session to see how some of that works. Any questions or observations about this?
Is there one we have in there that kind of like has like motion, like kind of that could detect motion?
Well, there is something called a and it also varies by kit, but there is one that if you know, a tilt detector, and I think this probably has that in here too, but without looking at the part list, did it have like a piece of paper with a part list?
Left it on my desk.
Yeah, that's fine. But there's another piece of paper that's going to have a picture for every one of these different parts that's in the kit, and it's going to give you at least a little bit of an explanation. There's probably, they may or may not have a CD anymore, and if they don't, it would be something that you could get online, that it would also give you the documentation for every one of the modules that they include in that kit. So here you can see all the different kind of LEDs that are available. so different colors. And so there's a lot of things that you have in the kit that I think you'll have a lot of fun playing with. And so my experience is a lot of folks really have a great time using the kit. And so I really want to have you all to have that kind of an experience. Any other questions? So I get extra credit if I can make everything fit back in the box, so.
Let me ask, what is that little board right next to it? It's the one on the.
This one,
Yeah,
that's the thing that I would want to get that piece of paper to be, I think this is, another adjunct board that it gives more specific capabilities that aren't on this board, and so it may be a daughter board where you clip on it, or it may just be a separate board. So it kind of looks like a mini Arduino, if you will. And so I don't want to overstate and say it wrong, so I'm not going to say if that's for sure what it is.
okay.
So, all right. Thank you very much.
Yeah.
Any other comments or questions that people have? If not, it's a good breaking point for today. And what we'll do on Thursday, I'll work on a little bit harder to try and get everything to fit, unless you're better at puzzles than I am. So, all right. All right. Thank you very much, everybody. Let me just check and see for those that are online, if there's any comments or questions. Okay, then I'll go ahead and stop the recording, and I'll stick around for a little bit if anybody has any questions they want to ask me, and I'll look forward to seeing you all on Thursday. Yeah, sure.
What would be the advantages of using something like a Raspberry Pi